Hi, this is going to be a much shorter unit, the second unit on learning theory. We're basically going to do two things. We're going to do compression bound or distillation, just pointing out the importance of that effect on the bounds. And the second thing we're going to do is the PAC-Bayes bound, which is moving from discrete models like programs, countable models, to continuous parameter models, which is important, of course, for deep learning, where we're setting continuous parameters. Okay, so compression or distillation. So now I want to think about some model, and I've written phi here to suggest a model that's defined by settings of parameters. And I'm going to let this denote how many bits it takes after we've compressed the model somehow. So I can imagine, I have a model in terms of floating point numbers. I pass it through some compression algorithm. And now I want to talk about the number of bits in its compressed form. So the idea is that if this is a lossless compression, I can always decompress. And that means I can take my probability distribution not to be defined on the source code, but to be defined on the compressed version. So really what we're talking about in the Occam bound, this is the Occam bound again, really what we're talking about here, or can be talking about here, is the compressed version of the file. Now, in deep learning, we often do something called distillation, which is you train a large model, and then you train a much smaller model to mimic the behavior of the large model. And this is a kind of compression algorithm that's called distillation. And there's some empirical results recently that use this distillation method to get strong generalization bounds, learning theory generalization bounds. And I'll mention that paper at the end of this unit. Okay, so now let's talk about the second loose end, and that is the move from discrete programs, discrete models, to continuous models. And so we're thinking now about parameters, some vector space, and our models are points in this R to the D. And instead of picking a particular point, note that a particular point has zero probability. So if I just talk about the number of bits it takes to name a point in a vector space, or to name even a single real number, it's an infinite number of bits. So that Occam bound just doesn't work, because log probability, the probability is zero, the number of bits is infinite, the bound is vacuous. Instead, what we're going to do is we're going to still consider a prior probability over our continuous models, over our vector space. But we're going to, instead of considering a particular point, we're going to consider a posterior distribution. So we're going to take our training data and use the training data to warp the prior into a posterior. The word posterior is a little perhaps inappropriate here, because the theorem is not actually doing any kind of Bayesian inference. Let me say what the theorem says. So let P be a prior and let Q be a posterior. So posterior is in quotes. Q is any distribution. P is a prior, Q is any other distribution. And what the theorem is going to say is that with high probability over the draw of the training data, it's going to be simultaneously true over all posterior distributions. So we're replacing the being simultaneously true over all programs with being simultaneously true over all possible posterior distributions, over all possible distributions. You don't even need the word posterior. So for any distribution Q, the generalization loss of Q, so now the generalization loss is going to be the average loss when I draw a point from the population distribution and a model from the distribution Q of the loss of that model on that point. So that's the loss of the distribution Q. You can think of this as like a stochastic rule, where you draw a rule from Q and then take the loss for that rule. And that's guaranteed to be less than or equal to, we have the same expression in terms of lambda that we had before. So I'm using the lambda twice here. And before I just set lambda to 5, which will still work here. But in place of the log probability of the model, which is what I had before, I have the KL divergence from the posterior, from this Q to the prior. So if Q is the prior, this term is 0. And if this was a discrete distribution and this was focused on one point, then this agrees with the previous theorem. This just becomes minus log the prior of that point. But now this works for continuous distributions. And in particular, this is going to let us analyze the case where the prior is a Gaussian centered around the initialization, and the posterior is a Gaussian centered around some other point. So, so now what I can do is I can look at a particular, suppose our model, our training algorithm decides it's got a particular parameter vector that it's learned. This is the output of our learning. I can define the loss of this. I can define it to be stochastic, where I draw from the population and I draw a noise vector, and then I add the noise vector. And by drawing a noise vector and adding it to the noise vector, I'm getting a distribution over parameter space that's Gaussian, centered around this thing I learned. There's a sigma in this that's saying how diffuse that Gaussian is. And I similarly define the loss on the training data the same way by adding noise. So I'm looking at the same distribution in parameter space. However, this is defined by drawing from the training data rather than the population data. So now what I want to do is I want to relate the error when on the test data, on the population. I want to bound that in terms of the error on the training data plus this penalty. And what's going to happen is I'm going to take that KL divergence, which was true in complete generality for any prior and any other distribution, any other posterior distribution, and I'm going to plug in this case and we get this bound. So now this looks an awful lot like the Bayesian analysis of L2 regularization. And I've sort of centered it at the initialization because I like to do that. So this connection between frequentist guarantees that don't make any assumptions about the prior and the Bayesian analysis that assumes the prior, that the data is actually generated by drawing models from the prior, still agree to, in a very strong way. The form of these bounds is very similar. It's essentially the same. But this bound can now be used with deep learning, right? Because deep learning is learning a parameter, and we've got this bound from deep learning. And now there's this recent paper, ICLEAR 2019, so it appeared a little over a year ago at ICLEAR, that uses both distillation and the PAC-Bayesian approach, the PAC-Bayesian bounds, where you're working with continuous parameter space, to get non-vacuous generalization guarantees. What does it mean to be non-vacuous? This is something that people have complained about for a long time. If you look at the generalization guarantees that are typically produced by learning theory, and you plug in numbers of an actual application, if let's say you're talking about error rate, the error rate can't be larger than 1. You know, if you get it wrong every time, your error rate is 1. But the guarantee provided by the bound, if you plug in the numbers of the application, is much larger than 1. So that's called, that makes the bound vacuous. The bound is saying nothing about the actual case in practice that's being used. However, this paper shows that using both distillation and the PAC-Bayesian formulation that applies to continuous parameters, you can get non-vacuous bounds for deep learning at an ImageNet scale, for ImageNet models. This was progress on a previous paper that had shown similar things for MNIST, and this made the leap to ImageNet. So what this is saying is that what the theory that I've just done is getting the tightest bounds that are known for deep learning models, the tightest generalization guarantees. They're still far from the observed generalization. So there's still something they're not capturing or not understanding. And I'm going to talk about what it might be that they're not capturing and not understanding in the next unit. Thank you.